Good morning, everyone. Thanks for inviting me here. As Michael said, I'll be talking about prospects for using BHEX to study extragalactic transients, which I think is quite an exciting topic. So just to set the stage, extragalactic transients can radiate across the entire electromagnetic spectrum. They are diverse, but just as a general rule of thumb, they can have thermal and non-thermal emission. So the thermal emission, for example, the photosphere of a supernova is often best observed in the optical band. And then the non-thermal emission comes from the collision of the supernova debris, or in some cases, a relativistic jet with the ambient medium. And that medium can be the circumstellar medium, which is sort of produced by the star prior to its explosion. And in some cases, we can track these even out kind of into the interstellar medium. And this non-thermal emission is usually observed, studied in the X-rays and the radio band. And the speeds of these components can be very different. So for the same supernova, you could have this very slow subrelativistic thermal photosphere. But then say if it has a gamma ray burst, you could also have a highly relativistic jet that shows up in the radio band. So for transients that say have relativistic jets, gamma ray bursts, tidal disruption events, which we started to hear a bit about from Jenny, it's really important to study these using radio observations. And there's a long history of doing this. What I'm showing here are some very detailed multi-frequency observations of a jetted tidal disruption event spanning 5 days after the discovery to a couple thousand days. And what I want to just point out here is that, at early times, the SED is really peaking in the millimeter to submillimeter band. And actually at 5 days, 10 days, that peak is not even being resolved. What does one do with these sorts of observations? Just kind of a high-level summary. These types of radio observations are really the only way to get at the energetics and the structure of the outflow, so the collimation, the total energy, and it's the best way to do kind of tomography of the environment. And for massive stars like supernovae, this is very important for learning about their mass loss history. And there's this whole decades-long history of trying to understand which events are coming from binary systems versus single stars. Those different progenitor channels show up differently in what the ambient medium looks like. And for TDEs to use these observations to study the small-scale environments around the supermassive black hole. So for the vast majority of transients with radio observations, what one is doing is trying to model the time evolution of that radio SED that I showed you. But there are kind of fundamental limitations to what you can do. There are just degeneracies that you can't break between modeling parameters unless you have VLBI. So radio VLBI can give you a direct measurement of the source size. It can demonstrate that an object has relativistic motion through observations of the expansion speed and or the proper motion. And it can help you study the morphology of the radio emitting material. So I'm showing here a very famous example. This was the binary neutron star merger GW 170817, for which centimeter wave VLBI established the presence of an off-axis jet. And this was really important because, it was hard to tell otherwise in modeling whether there was truly this successful jet or if the jet was choked inside the system. But unfortunately, despite their importance for breaking these modeling degeneracies, VLBI observations are only available for a handful of extragalactic transients, although I'd say it's starting to become more common to get this kind of data. Okay, so now relevant for BHEX. So centimeter wave observations are very well established for different classes of extragalactic transients. So this is this two-panel figure shows centimeter wave data on the right for various classes of transients. It's historically been much less common to get observations at high frequencies for a number of reasons. Just facilities used to be not sufficiently sensitive. The millimeter emission tends to be faster. So if you remember the SED evolution of the TDE that I showed, at early times it peaks in the millimeter band, but that shifts to lower frequencies within a few weeks, but for some events it's even within a few days. And it just used to be that our surveys would not discover transients early enough for it to be really worth it to try observing them with a millimeter telescope. And then I would also say that we just didn't really know which objects were likely to have millimeter emission. We're primarily selecting these, say, in the optical band, and we didn't really know what sorts of optical signatures were predictive of millimeter or even radio emission. But this is changing now. So one of the developments that I want to sort of bring to your attention today is that the landscape of transient discovery has changed a lot. And I think that presents good opportunities for BEX. So in the optical band, we are now routinely discovering transients when they're very young, within the first day, which is exactly the timescales that you would want to be able to trigger millimeter observatories. And then there has been an expansion of transient discovery across the electromagnetic spectrum. All of the facilities that I'm showing here are highly relevant for selecting the sorts of sources you'd want to observe with a telescope like BEX. There are even surveys that are starting to do the first wide field blind discovery of transients directly in the millimeter and submillimeter band. They're doing this for CMB measurements, but along the way, they're basically doing a high cadence time domain survey. So one of the developments that has come out of this changing landscape is the discovery of transients that really are millimeter transients. So for really the bulk of their radio evolution, when they're still bright, the radio SEDs peak at very high frequencies. This is one of the very famous objects. It's called AT2018 COW, sometimes nicknamed the cow. And what I'm showing here is the millimeter light curve. So this is some millimeter array measurements at 230 gigahertz and 340 gigahertz. The emission's completely self-absorbed at APCA frequencies of 34 gigahertz. This is for the first month or so post-explosion. And you can see this was 50 millijanskis for almost a month. So an extremely bright event that would have been a great target for millimeter VLVI. But unfortunately, this caught us by surprise at the time. This is another well-known object, AT2022 CMC. So this was very likely a jetted tidal disruption event. It's the highest redshift such object discovered to date, but it was actually found by an optical time domain survey. These are pretty rare events. So this is one of only a handful of such objects studied in any detail. And I'm showing here the evolution of the radio SED. So I triggered some NOEMA and SMA observations for this event, and it really peaked at high frequencies for a long time. And what I would actually say is at this point, you can ask the question, why did this event peak at such high frequencies for so long? Why is it different from other sorts of transients that we see? And I don't think we actually know the answer to that. There's some possibilities. So one possibility is that for certain transients, so such as 18 cow, if you have a very dense environment surrounding the progenitor, and that would be expected if you had a binary evolution channel. For example, if the transient was triggered by a binary merger, say a merger of a black hole and a Wolf-Rayet star, which is what's being shown in this cartoon here. If that happens, then when the shock slams into the surrounding medium, you will end up with higher magnetic field strengths, and you could, in the basic kind of synchrotron model for the radio emission, you would expect to have a higher peak frequency or higher frequency for the synchrotron self-absorption frequency. So maybe that's why we see millimeter peaking emission for these events. For the TDEs, it has also been speculated that that what we're seeing in the millimeter band is a component of the jet called the reverse shock. So that is from the as the jet impinges on the surrounding medium, you get a shock traveling outward into the medium called the forward shock, but then you also get a shock traveling into the jet itself called the reverse shock. And if that's the case, that's very interesting because you can use this reverse shock to actually study physical properties of the jet that are very difficult to get at otherwise. But yeah, I would say we don't totally know that that's the case yet. And then there are other suggestions that in the millimeter band, for some of these kind of transrelativistic explosions, you're seeing different populations of radiating electrons than you're seeing in the regular subrelativistic supernovae. So that can also be a reason why these events look so different in the millimeter band from kind of more conventional supernovae that we've known about for a long time. So just to kind of summarize this slide, I would just say that we've seen observationally that a number of classes of interesting transients really peak in the millimeter band, and trying to interpret that and understand why they do has actually been quite fruitful and led to a lot of really interesting areas of theoretical investigation. All right, so I've already mentioned this, that VLBI is the best way to break certain degeneracies in trying to do physical modeling. This is a plot of the centimeter wave light curve of a supernova, a special type of supernova, the type known to be associated with long duration gamma ray bursts. And there's been this long, decades-long quest at this point to find off-axis gamma ray burst jets in these supernovae. But it's actually one of the big difficulties is that you see luminous radio emission in a number of these objects, but actually proving that what you're seeing is a jet versus just circumstellar interaction is really not trivial. So I won't go into the details. You can see lines, solid line, dashed line, dotted line. This is the authors trying to figure out, could this be a jet or is this just CSM interaction? And it's actually very difficult. And so really what you need to do, you want to get VLBI as the best way to determine whether you're really seeing relativistic motion or not. Okay, so for BHEX itself, so what I'm envisioning is that BHEX would be used to do VLBI at millimeter wavelengths for some of these transients where the radio emission peaks at very high frequencies. I see that as a really interesting frontier in transient science. So this is just a summary of a quick calculation that I did, making a couple of assumptions that maybe I should update. I see what I learned at the conference today. But just for 18 cow, I think it's reasonable to think that there will be about one per year that would be suitable for BEX. And for these jetted TDEs, potentially the number could actually be very high. There's a lot of uncertainty on this rate, but it could be the case where we would actually be limited more by how much time we want to spend with BEX rather than the number of sources that are available to us. And we're only getting more efficient at discovering these sorts of transients. So I'd say that in a way, this is kind of a lower limit. So I want to say more now about these surveys. I've talked about some specific transient classes where we kind of know what they are to some extent, and we're just trying to get more information about them. But I think another interesting opportunity for BEX is that, as I said, we now have some of the first wide field surveys that are blindly looking for transients at these high frequencies, and primarily for cosmology. So the South Pole Telescope has been doing this for many years now. It's been doing what I would call a high cadence time domain survey from the South Pole across about 1,500 square degrees. And the SPT collaboration has done a lot of really careful work in measuring the rates of transients. They've discovered dozens of flares from nearby stars, as well as a number of transients that are likely extragalactic in origin, but of unknown nature. This year, the Simons Observatory has had first light. It is doing what I would call an all-sky high cadence survey from Chile. So about 10 times the area of SPT at a wide range of frequencies. Early science operations actually have basically begun, and it is funded to produce a transient alert pipeline within the next few years. So blindly discovering transients is one of the main goals of this facility. So just again, some very rough rate estimates. It's hard to say because we don't really know what the sky has at these high frequencies. But SVT has found several of what I would say are probably extragalactic transients in their footprint. And if you just assume SO should have roughly a similar sensitivity, but it has a 10 times larger footprint. So the rate should be about roughly 10 times larger than that. So that's just a rough estimate of, again, what might be available for observations with BEX. And any transient discovered by such a facility would be very bright because they're pretty shallow surveys. So the limit, they have to be at least around 20 millijanskis or so. Okay, so what can we actually learn scientifically? So I think there are a few types of questions that I'd be interested in using BEX to answer. One is to understand progenitors. So some of these transients, like 18 cow, we have some ideas for what it could be, but some of the different models, make different predictions in terms of the nature of the outflow that you might expect to see. And so getting direct VLBI observations could help us break the degeneracy between some of these different model scenarios. For jetted TDEs, there's a lot of interest in studying the dynamics and properties of their jets. And again, one of the best ways to do that is with VLBI. And these events their radio emission does peak at millimeter wavelengths at the earliest times. And then finally, I'm hopeful that in the next few years, we'll be discovering entirely new and unexpected types of transients with millimeter surveys. And so we'll be trying to model their emission, figure out what they could be. And again, VLBI is critical for that. Okay, so just to summarize, I talked about a couple of recent developments in time domain astronomy, the discovery of various classes of transients that really peak in the millimeter and submillimeter band. The reasons for that behavior are all interesting, and we're still trying to figure out exactly what's going on in these systems physically. We also have the first wide field surveys at these high frequencies. VLBI has had a longstanding role in transient astronomy at centimeter wavelengths, helping us to break degeneracies in in physical modeling. But what's happening now is that we have a need for millimeter VLBI. And for some of these types of objects, given their high brightness temperatures, I think that BHEX would be in a very good position to help us solve some of the mysteries about their nature. And with that, I'll just leave up the summary slide and take any questions.
Thank you so much. Question from Yuri, go for it.
Thank you.
Oh,
Sorry, yes, I trust that you
yeah,
can hear me now.
Yeah.
So actually, I have two questions, one scientific, one operational. Let's start from scientific one. Thank you for a great and compact review of this extremely exciting field. So you understand that having high BHEX frequencies like 100 or 300 gigahertz, if we are lucky with sensitivity so that your transient is bright enough, do you prefer to observe around the peak or higher than the peak? So do you prefer to be able to actually see through your blob or whatever this is, right? To resolve it, and will you be able to distinguish between several possibilities like shocks or jets? Or you still prefer to be at the peak in the partly opaque regime, and why?
Yeah, that's a good question. To be honest, in doing these calculations, since we're so sort of sensitivity limited, I just took the peak because that's where I would be most optimistic about detecting it. But just in terms of if I had the option, I mean, I think you would want ideally to do this at multiple frequencies. So it'd be nice to get close to the peak, but also even above the peak. If it's a relativistic jet, then you could start to see actually start to get at the structure of that jet. So that would ideally, I think, if it was really bright enough, I would want to do this at multiple frequencies. But in practice, I imagine that we would probably be trying to do this right around the peak of the SED.
Thank you. And operational question. I will not go into details, but clearly it is important how far in advance can you trigger BHEX, or trigger is probably here a wrong word, at least to get BHEX interested. And for centimeter, this is kind of very friendly with VLBI observers, right? Or VLBI networks, because you have the delay sometimes like years, right? And the 2018 cow is also in that regard kind of positive, because the peak was more than a month away. So what is a typical realistic delay between a discovery of a transient and the moment when you want to observe it?
I think weeks for these sorts of objects, these TDEs, 18 cow, weeks would actually be fine. So yeah, that's what I would say. Maybe just going through a few of the obviously in my head. Yeah, I think a couple of weeks.
Okay, thank you.
Joseph, go for it.
Thanks. Can you hear me okay?
Yes.
Yeah.
Sweet. Yeah, that was such a cool talk. As someone who's like in the transient and radio VLBI world, I was absolutely enthralled. So I had two quick questions. So the first was for objects that are very nearby, like for example, core collapse supernovae under 10 megaparsecs, we have objects like 23 IXF with radio detections. Do you think there's any hope that we can resolve the ejecta for these kinds of supernovae that are very close by? I know that like 23XF didn't have detections at 230 gigahertz, but it had a lot of emission at lower frequencies. And so I'm wondering for these very nearby objects with BEX, what do you think the hope is for resolving the ejecta like we do with 93J?
Right. Yeah, so that's a good question. I mean, that would be obviously really scientifically interesting to do. I think the problem is that for these nearby supernovae, I mean, they are very interesting in the millimeter band. They're just very faint. So I think that would be tough. I just think they're not, for the most part, they won't be bright enough. And then we would have to be really quick. So then we'd be talking about a day or so. But I think, yeah, so they'd be very faint. We're talking about much faster. I looked into also for this Nove, which also are very interesting in the millimeter band. And there are suggestions that some of the millimeter emission is powered by shocks. And yeah, they're actually very interesting. But also in that case, again, in that case, their brightness temperatures are, I think, quite a bit lower than the regime that is kind of the sweet spot where BEX can do something unique. So I think that for BEX, maybe the prime targets are these more sort of relativistic events with very, very high millimeter luminosities.
Yeah, that leads into my second question, which is so you mentioned that we're now getting transients discovered under 24 hours post explosion. With just in the last couple of years, we've seen objects that are discovered 3 hours post explosion, or even 1 hour for the 1As, which I know aren't really relevant for the radio question. Do you think BEX could benefit from a target of opportunity triggering system? We get these alerts from Rubin within 60 seconds. With other objects, we can get spectra within 6 hours. Is it worth a dedicated system for triggering on these early objects? Like you said, we need to catch them within the first day to kind of be able to see the radio emission with BEX. Is that something that you think has a broad enough a set of objects or expected transients that you think that should be something worth looking into for BEX?
Yeah, that's a good question. So I think that if you say, I mean, kind of what you're asking is, could there be something that we're not really anticipating where it turns out there's some transient class with spectacularly bright millimeter emission on a short time scale, and so somebody might come in and try to trigger BEX for their source. I mean, if something really has daytime scale bright millimeter emission, I would expect it to be picked up by one of these CMB surveys. So in a way, the most direct way to look for something like that is in the millimeter. Science Observatory will do a 1-day cadence survey of pretty much the whole sky overlapping with Rubin. And the limiting flux density there is nicely sort of complementary to what BEX wants to do. So to detect them, they'll have to be already 20 plus millijanskis. So I would think that being prepared to maybe trigger off of something detected there, if we could convince ourselves that it truly is extragalactic, maybe would make more sense than planning to sort of find something with a survey, follow it up with a millimeter telescope, finding that it's bright, and then trigger BEX. I don't know if that totally answers your question, but.
Yeah, that's great. Thank you so much.
Maybe just add briefly to that, there are a lot of potential observables in these situations. I was curious how anisotropic you would expect these kind of marginally events to be. And that's related to the idea of, do we just need 1 or 2 ground telescopes with BEX, or is imaging really necessary? What do you think the real critical measurements are? Are they, full imaging, or just a brightness temperature, or a spectral structure? What would you go for first?
I mean, I think just a direct source size measurement would be extremely useful for a couple of these where, like I said, we don't even know that is one of the modeling parameters that's then degenerate with a whole bunch of other things. And so if
Yeah.
you could actually just resolve it and measure the size, that's the first thing that I would try to do.